In this chapter, let's study electrolytes. We know that some solids and liquids are soluble in polar solvents such as water. For example, sucrose and sodium chloride are both soluble in water. However, scientists found that different aqueous solutions have distinct electric conductivities. For example, the sucrose aqueous solution has poor electric conductivity, close to that of pure water. In contrast, the sodium chloride aqueous solution has much higher electric conductivity than pure water. To explain the difference in conductivities of aqueous solutions, the concept of electrolyte was introduced by Arrhenius. He stated that an electrolyte is a medium containing ions and conducts electricity through the movement of them. For example, silver iodide is a solid-state electrolyte. At room temperature and in thermodynamic equilibrium, a small fraction of silver ions are displaced from their regular lattice sites into interstitial positions. When an external electric field is applied to silver iodide, an electrostatic force in the direction of the electric field is exerted on silver cations. The interstitial silver cations move in the direction of electric field and may fill the defects. Meanwhile, silver's atom in their regular lattice site may move in the direction of the electric field and leave defects behind them. Thus, both the interstitial ions and the defects conduct electricity. They resemble the conductivities of electrons and holes in semiconductors. Ionic liquids are another type of electrolytes. They are in liquid phase near room temperature and are composed of ions. For example, 1-butyl-3-methylimidazolium hexafluorophosphate is a typical ionic liquid at room temperature. Its cations and anions are free to move at room temperature. In external electric field, they move in opposite directions to conduct electricity. Molten salts are electrolytes at high temperature. For example, sodium hexafluoroaluminate, also known as the mineral cryolite, have movable sodium cations and hexafluoroaluminate anions. Cryolite is used as a solvent for the electrolysis of aluminium oxides such as bauxite. The most important electrolytes are the electrolytes in the form of solutions. When some solutes are dissolved in polar solvents, they dissociate into ions. Sodium chloride aqueous solution is a typical electrolyte solution. Solid sodium chloride is an ionic crystal. When it is dissolved in water, the ions mix with the water molecules and become free to move. Hydrogen chloride aqueous solution is another typical electrolyte solution. A hydrogen chloride molecule has a covalent bond. When it is dissolved in water, the molecules ionize into hydrogen cations and chloride anions. During dissociation and mixing, the mean distance between the cations and anions increases. That is, the electrostatic energy increases. Since the volume and pressure do not change significantly, the enthalpy increases. Meanwhile, the entropy increases during mixing. However, the increase of entropy cannot compensate the electrostatic energy increase to lower the Gibbs free energy. Otherwise, dissociation should take place even without solvent. The reason why some dissociation is spontaneous is that the solvation of ions lowers the enthalpy. Solvation is caused by the interaction of solvent with dissolved ions. In the process of solvation, ions are surrounded by a concentric shell of solvent due to the electrostatic interaction between ions and polar solvent molecules. Solvation by water is called hydration. The sign of the Gibbs free energy of dissociation depends on a competition between electrostatic energy, solvation energy, and entropy. Thus, dissociation is a reversible reaction. Let's consider the dissociation of a general electrolyte, Ca. C and A represent the cation and the anion, respectively. The dissociation constant is the equilibrium constant of dissociation. If the solute is a solid before dissociation, its activity is 1. The dissociation constant becomes the product of the activities of the ions, taking the Stomchi metric numbers of the ions into account as exponents. The dissociation constant of a solid determines the activities of the ions when they are in equilibrium with the solid. That is, it determines the solubility of the solid. Thus, the dissociation constant of a solid solute is called its solubility product. Let's take saturated calcium carbonate aqueous solution as an example. When dissolved, it dissociates into calcium and carbonate ions in 1:1 ratio. Its solubility product is a product of the activities of calcium and carbonate ions. Since the solubility product of calcium carbonate is very small, the saturated calcium carbonate solution is very dilute. Dilute solutions are close to ideal solutions. The activity of a dilute solute species is close to its numerical value of molarity with mole per liter as the unit. The molarities of calcium and carbonate ions are equal, so their activities are also equal. According to the definition of solubility product, the activities are equal to the square root of the solubility product. The concentrations of calcium and carbonate ions can be also calculated. Limestone is a common type of carbonate sedimentary rock. The dissolution and deposition of soluble rocks such as limestone formed a topography called karst. As water-containing carbon dioxide passes through limestone or other calcium carbonate-containing minerals, it dissolves part of the calcium carbonate, hence becomes richer in bicarbonate. As the groundwater enters the cave, the excess carbon dioxide is released from the solution of the bicarbonate, causing the much less soluble calcium carbonate to be deposited as stalactite, stalagmite, columns, and other speleothems within caves. By the way, solid calcium bicarbonate does not exist. Evaporating calcium bicarbonate solution to dryness yields the solid calcium carbonate. Calcium bicarbonate does not have a solubility product. Nevertheless, the above-mentioned reaction is still a valid chemical equilibrium between calcium carbonate, water, carbon dioxide and bicarbonate ion. Some undissociated electrolytes are soluble, such as sulfuric acid and acetic acid. Consider a simple compound, Ca. The stoichiometry numbers of the ions are both 1. Thus, the dissociation constant is the product of the activities of C and A divided by the activity of undissociated Ca. If Ca is the only solute in the solution, and the solution is dilute, the activities of A and C are identical. The activity of undissociated Ca is the difference between the initial activity of Ca and the activity of C or A. The initial activity of Ca is the hypothetical activity of Ca, supposing that it is completely dissolved but not dissociated at all. So, the dissociation constant is expressed in terms of the activity of C or A, and the initial activity of Ca. The dissociation degree is the fraction of solute that dissociates. Then, the dissociation constant is expressed in terms of the initial activity and the dissociation degree. This equation is called the law of dilution or Ostwald's dilution of law. It is a quadratic equation about the dissociation degree. In mathematics, the law of dilution has two solutions. However, one of the solutions is negative, which is impossible as a dissociation degree. The only possible solution is the positive one. Let's consider two extreme cases. A strong electrolyte is an electrolyte with huge dissociation constant. Thus, the dissociation degree of strong electrolytes is always close to 1. It means that the solute dissociates completely. A weak electrolyte is an electrolyte with tiny dissociation constant. The dissociation degree is inversely proportional to the square root of the initial activity of the solute. The dissociation constant is so small that most of the solute does not dissociate. Here, let's use mercury chloride as an example. It is soluble in water and forms a weak electrolyte. Given the initial concentration of mercury chloride, please find its dissociation degree and the concentration of chloride ion. First, we can find the initial activity of mercury chloride from its initial concentration. Then, calculate the dissociation degree using previous equation for weak electrolyte. Finally, convert the dissociation degree to the activity and concentration. Like other electric conductors, an electrolyte has its electric resistance. The electric resistance of a resistor is proportional to its length along the direction of the electric current and is inversely proportional to its cross-section area. The proportionality coefficient is the resistivity of the substance. The conductivity is the reciprocal of the resistivity. Without applied electric field, the ions move randomly. Therefore, on average, there will be no overall motion of ions over time. However, when an electric field is applied, each ion is accelerated by the electric field. On the other hand, the solution exerts a drag to the moving ion and the solvent molecules moving together with it. The result is that the ion moves with a finite average speed, called the drift speed. Different species of ions typically have different drift speeds in the same electrolyte solution. Electrical mobility is the ratio of drift speed to the electric field. It describes the ability of charged particles to move through a medium in response to an external electric field that is pulling them. The conductivity of one species of ions is proportional to the product of its concentration and electrical mobility. Please check the derivation by yourself with the help from the illustration. Molar ionic conductivity is the conductivity from one species of ions divided by its molar concentration, which is proportional to its electrical mobility. In infinite dilute electrolyte, the ions move independently. The molar ionic conductivity in infinite dilute electrolyte solution is called its limiting molar ionic conductivity. According to Stokes' law, the drag on a spherical object in a viscous liquid is proportional to its radius. On the other hand, the electric force is the product of its charge and the electric field. Thus, for the same value of charge, the limiting molar ionic conductivities of ions decrease with their radii. Here, I show you the radii and limiting molar ionic conductivities of some typical ions at 25 degrees Celsius. The order of the values for alkali metals is surprising, since it shows that the smallest lithium cation moves more slowly in a given electric field than sodium cation, which in turn moves more slowly than potassium cation. This occurs because of the effect of solvation of water molecules. The smaller lithium cation binds most strongly to about 4 water molecules, so that the moving cation species is effectively lithium tetrahydrate. The solvation is weaker for sodium cation and still weaker for potassium cation. The increase in halogen ion mobility from fluorine anion to chlorine anion to bromine anion is also due to decreasing solvation. Exceptionally high values are found for hydrogen cation and hydroxide anion, which are explained by the Grotthuss proton hopping mechanism for the movement of these ions. An excess proton or proton defect diffuses through the hydrogen bond network through the formation and concomitant cleavage of covalent bonds involving neighboring molecules. This hopping is much faster than the translation of ions. The electrical mobilities of the ions in an electrolyte solution are also influenced by the interaction between them. In the adjacency of one ion, the species of ions with the opposite sign of charge is more concentrated than those with the same sign of charge due to the electrostatic interaction. When an ion drifts in one direction, the nearby ions drift in the opposite direction. Thus, the shear stress between them, which can be understood as a kind of friction, slows down their motion. As a result, the mobilities of ions, as well as their molar ionic conductivities, decrease with ion concentrations. Kohlrausch's law of independent migration of ions states that the conductivity of an electrolyte is sum of the conductivities of all the ions. The molar conductivity of a solute is its conductivity of the electrolyte solution divided by the solute's molar concentration. In a strong electrolyte, the solute dissociates completely. So, the concentrations of the ions are proportional to the concentration of the solute. The molar conductivity is proportional to the total electrical mobilities of the ions, which decreases slowly with solute concentration. Based on experimental data, Friedrich Kohlrausch proposed the nonlinear law for strong electrolytes. It states that the decrease of ionic molar conductivity is proportional to the square root of the concentration. The proportionality coefficient is Kohlrausch coefficient. Here, the limiting molar conductivity is the total limiting molar ionic conductivity. In a weak electrolyte, the concentrations of ions are very low. Thus, the mobilities can be regarded as constants, and the molar ionic conductivities are the limiting molar ionic conductivities. However, in a weak electrolyte, the concentrations of ions are limited by the dissociation degree. Thus, the molar conductivity is equal to the product of the limiting molar conductivity and the dissociation degree. Pay attention that the dissociation degree of a weak electrolyte depends on the solute concentration. Here, I show you the molar conductivities at 18 degrees Celsius of a strong electrolyte, hydrochloric acid, and a weak electrolyte, acetic acid, at different solute concentrations. You can see how the molar conductivity of strong electrolyte depends weakly on concentration, while the molar conductivity of weak electrolyte depends strongly on concentration. The conductivity of a weak electrolyte can be used to determine its dissociation constant. Please check the example by yourself.